And then I encourage you throughout these two presentations to ask a lot of questions, because this is the technical AI workshops, and we're here to learn as much as possible and have like an interactive dialogue with the people who are presenting what they have been up to in machine learning or AI. And our first speaker is Rickard from iVisio, who is actually a good friend of mine, who's going to talk about semi-supervised learning. And as far as I understand, this has something to do with the application of classifying objects for Swedish railroad maintenance. So that's the background. I give it up to you, Rickard.
That will have to suffice. Right. Okay, does this work? Nice. Okay, so my name's Richard Löwenström. I'm working at a company called iVisio, which is an AI startup. We are currently working with automating inspection of the Swedish railroad systems. And in the upcoming project, we are looking into recognizing damages on these railroads. And this is why we've looked into MixMatch recently, in order to, because there's often very few observations of these damages. Yes, and today I will try and share what I've learned so far, and try and show that it's pretty easy to implement, and I hope that you will find it interesting enough to try it yourselves. I think it should be pretty straightforward and maybe go quite quickly, so if you have any questions, please ask as we go along. So, if you didn't know, semi-supervised learning is like when you do normal supervised learning with a labeled data set, but you add in unlabeled data and try to learn something from this unlabeled data as well. And earlier this year, they released a paper about MixMatch from Google, which which basically had very good results with semi-supervised learning, using basically a 10th or a 20th of the full labeled data set on CIFAR and street house view numbers, and got very good results.
Sorry, by labeled data, you mean that is prediction of categories, and you're mixing the prediction, or that some of the input features are missing?
No, sorry. It's not it's not that we have missing data. So it's not that we're filling in missing data like that. But well, in one sense, I guess it is. But we have fully unlabeled data. So it's not just like a part of the data that's unlabeled. If I understand your question.
Yes. So you're doing classification. But you don't have the label of that particular data.
Exactly.
Point.
Yeah.
Okay.
So for example, in Kaggle, you might have a training data set with labels and a validation data, or it is a test data set that you don't have any labels for at all, but you could use that data set to train on unsupervised. Okay.
I'm just curious about these slides right here. Do you know what is the fraction of data points used if you compare it to this full supervised?
Yeah, so I think it's like 50,000 data points in the full data set on CIFAR, and like 73,000 in the street house view numbers. But yeah, so you can compare, like the blue line there in the bottom is for the full data set, and you can look at mix-up, the dark red is the supervised with mix-up. Yeah, so you have an idea of the difference. Okay, so I want to jump into code pretty soon, because I think that's a nice way of understanding something. Like, as a brief summary of MixMatch is that there are basically two main components. It's supervised mix-up, where it's mix-up, which is where you have two images and their labels, and you weight them together by a weighted sum to create a new image and a new label. And the second component is label guessing, which is when you have a model and you predict what the label might be for this image, and you use that to train on. And what they do in MixMatch is they make multiple augmentations of the same image, and they make one prediction for each of these augmented images, and they average together the final guess. And finally, they also sharpen the prediction, so they pretend that their prediction is they're more certain of their prediction than they actually are. And I guess the idea behind this is to create some sort of clustering. So like an attempt at an analogy might be like in math, where you have axioms that you postulate, and then you can make lots of proofs based on these axioms and build gradually from there. It's the same idea maybe with having labeled data as the axioms and then trying to spread this knowledge to the unlabeled data points. Yes. So let's do this. Okay, so we created I should zoom in, sorry. Is that okay? Yeah, so we created a toy problem in order to try out MixMatch and make an implementation that we can bring with us to another problem. So we took just using MNIST, which is pretty similar to street view numbers, I guess. But it's a very simple problem, so we need to remove a lot of images in order to make it hard enough that MixMatch, like supervised, is pretty good at even a few images if you do a lot of augmentations. So we're just having 1.2, like one image per number in MNIST when we're training. So this is TensorFlow 2. I think it's pretty similar to TensorFlow 1. It's just a cleanup, I think. I will try to share the code afterwards. We have our trusted MNIST dataset, and we're just doing simple augmentations. These are a few examples. We're doing rotation, some translation, zooming, and shearing. And this is used for all the augmentations we do. And then we have an example of how mix-up would work then. Just mix-up that you might use in supervised learning as well. So you have two images, and you choose a weight cube between 0 and 1, and you just weight them together by 0.8 then and 0.2, and then you have an image that looks something like this. Sorry?
Could you just explain why you do these transformations and augmentation? Is that generally how it works?
So since we only have a single image of each digit from 0 to 9, we basically have no data. So the model could learn this by just looking at, if this pixel is filled in, then it's a 9 or something. So what we're doing lots of augmentation is to make the data set, is to make it a more realistic use case. Because in normal cases, when you do supervised training, you're always doing augmentation. So I wanted to make a toy problem where I compared to a realistic supervised solution with MixMatch. Yeah, did that answer your question?
I just wanted it to be on a very simple level, that you always do augmentation so that you can train better models.
Yeah, so it's basically just to get more data, sort of. Right? So we only have one digit for lots of the one example of each digit, basically. But then we basically get tons and tons of new types of fives that we didn't have before. And as long as we still think it looks like a 5, then it's maybe useful. Yes, sir?
How many data you have in the end of the implementation?
Now I'm doing it dynamically, so I have like an infinite number of degrees, for example. So, but I mean the additional information in each new like variation of rotation won't be that much. The idea is to make it rotation invariant, I guess. So it should detect a 5 even if it's a bit rotated. And I think sharing is a really good augmentation since we only have a single image of each digit. Yeah? So this is just an example where I've chosen Q. This is what we do later. But this is like, if we picked 0.8, this is what the image would look like. And it's not super obvious that this is a good idea, I think. Like in my intuition, this might work better for sound. For example, if you have a voice and you overlay with another voice, you can sort of hear both of the voices at the same time. I guess it sort of works for images as well, that you can see a cat inside a dog, like faded or something, but yeah.
I know that in computer vision you usually change the background if you want to augment the data, but I cannot see what's the point of mixing with a specific other label. I mean,
yeah.
What's the added value of using this instead of changing the background with anything other than that?
I think change the background in this particular case won't help on the test data set or the validation data set because it's always black in the background, right? But I agree if we wanted to move it to production where in reality we sometimes had noise in the background, then we would definitely want to do what you're saying. I think that's a more realistic approach. But for mix-up, the idea, I think, from what I've read, is that it's regularizing. They want a linear behavior between two images. So if I fade from one image to another image, they want to have like reasonable behavior between those two. And they think like just moving the labels like linearly from one to the other is reasonable. And it's shown to work very well. But I agree that it's not super intuitive, that this is a good idea. Yes.
Can you scroll up again and show the code that did this?
Yeah, this is just two images and I weigh them together. That's just.
And there's a 5 and there's something else.
It's a 7.
A 7.
It's a 7. Yeah. Both are augmented, so it looks different each time, right? So. Yeah. So, and the weights we use in MixMatch, or in MixUp actually, or what they used in, you can use any weight function, but in MixMatch they used a beta distribution, and they set alpha and beta both to 0.5. And but they only use the upper part. They mirror the output, so they favor the first image in the mix-up. So if we have image 1 and 2 again, then we would have much more weight on the first image than on the second image. And I can show you the distribution. So we have a lot more focus on the first image. It's almost like a lot of time above 80%, but we also have quite a lot of probability mass on like the lower numbers. So we might sometimes weight the images quite equally. So when we combine them together, I can show you a couple of examples. Like I said, it's not super obvious that this is a good idea to mix up like this, but yeah. That's what the data will look like for the model when it's training. And we also do the same, right, with the predicted labels, or with the actual labels as well. So if we have we do the same with the labels. And then after we do that with the labels, we make lots of predictions for the same image that we augmented in different ways, right? And then after we've averaged those together, we do sharpening on the label and on the guessed label, and we pretend that we're more certain than we actually are. And this makes sense sort of when you're training that you want it to move towards being more and more certain all the time. So here we have the blue will be the guessed label, and we try to make the model be more certain with and we sharpen the blue labels to become the yellow labels instead. Yes. Yeah.
So are you saying that you're taking the labels, the P are the labels, which is just the Q on one and 1 minus Q on the other one? And then
no,
you're taking the probability
no,
of the
sorry.
network.
No, so when I'm doing the labels, I'm just doing the same thing as with the images, right? So for each image, I have guessed the label. So I'm guessing 10, for example, I might guess 10 labels for the same image with 10 different augmentations. And then I take the average of those. So I just have like a bunch of different probabilities, and I take the average for each, like over the axis of the batch.
Right, so here we're not talking about training, but when we're doing the predictions.
Yes, this is the predictions that we will train on.
Okay.
Yeah, so this is creating the unlabeled data set.
Right.
So the predicted data set. Yep.
And looking at results for this sample picture or for the whole
No,
sample?
this is just some random Dirichlet numbers. So I'm just making up an example to show what happens when we sharpen probabilities. Right, so what numbers will actually come out will depend on the model, right? And it's deterministic. So we will just input some image, and we will get out some probabilities, and we will try and force the model's probabilities to be more like certain that it's a certain class, rather than being a spread over multiple classes.
That's interesting to note that you're sharpening the probabilities, but you're still training on the smooth label with some probabilities of the other classes, right?
No, I'm training on this sharpened image, right?
Yeah, but the sharpen is not a threshold at like max.
No, we're not doing, but you can do argmax. That's something I tried and it works pretty well.
So I mean, that's sort of the naive approach, that you just do label propagation. You predict something and then you take the max, and then you have sort of your labels.
Yeah, but that can actually work.
Yeah,
okay,
but I mean, that doesn't work. This is obviously better because that's a very naive approach, and there are several reasons why that doesn't work.
Actually,
it's sort of interesting. So sharpening is sort of a intermediate of taking the output of the network and actually taking the max of the output.
Sure.
So it's sort of
yeah, but there's, like you said, like you can do different types of sharpening. So this is just the one they use in MixMatch. But there's obviously like tons of different, anything that maps to 0 and 1 would work. So any distribution function would work to use for sharpening. So in the paper they use exponent to the power of 2. What they call it temperature. Temperature is a half. But, yeah. But I found that exponent 6 works best. So it's pretty close to argmax actually, to have to the power of 6. At least if the model is a bit more certain than this random Dirichlet output. You see, if it's just a bit more certain about one label, it will pretty much be argmax in this case. Okay, so I'm not sure we will go into depth on this so much, but I just wanted to show that it's not that much code to just create the unlabeled dataset, predictions for the unlabeled dataset. To try and use in your model. So here we're just doing we have the validation data set. We're throwing away all the labels on the validation data set. And we're repeating each image k number of times. We're augmenting each of these images, and then we're predicting the maybe I can show here. We're predicting for each image what we're guessing the label basically, and here we take the reduced means, we take the average over the axis, and then finally we sharpen the predictions. And in the end we take these predictions and we merge it with the original image that we had, and then we augment that image another way than we did with the ones with the augmentations we did before that we used prediction on.
I'm wondering, when you're creating the predictions, you have a previous model that you only trained with this very small set of data, right?
No, I'm doing this dynamically during training. So like every epoch, for example, you might update, or actually I'm doing it dynamically all the time. So every batch I'm getting, I'm using the latest model all the time. Yeah.
I'm confused about that, I guess, as well. So first, before this, you train the network in some label data.
No, the network starts untrained.
At all.
So it's guessing like just randomly, so like uniformly from the beginning, I guess, like on average for each. So it doesn't have any idea what any image means.
But you're mixing in some label data, is that correct?
Yeah, I'm also doing label data. Yeah, but this is just for how easy it is to create the unlabeled, the guessed data set that we have guessed labels on.
Fair enough.
And in what fraction, maybe I'm skipping ahead now, but how large fraction is labeled data and unlabeled data when you train?
Here, I have a single image. On the hardest problem, we only have a single image per digit.
Right.
And then we have like 30,000, I don't remember how much is in MNIST, but like 30,000 unlabeled images or something.
But through each epoch, you're generating a few like unlabeled ones, and you combine it with a few...
No, I'm doing it all the time. So,
right.
like
But on average, what's the ratio between those two?
like in my batch that I'm training on?
Yes, exactly.
But that's the hyperparameter that I'm choosing here. Right?
I'm
So I'm doing a hyperparameter search to see what mix of using, like, so here I'm calling the data set supervised and unsupervised, but it might be better to call them labeled and unlabeled data set. Yeah, sorry.
So aren't you, by doing this, aren't you like reinforcing whatever bias learned already, and then you just like, and isn't this like a positive kind of feedback loop that you...
Yes, it is. It is. Definitely is.
And is that a problem?
It might be a problem, right? Because if you have unlabeled data and you start propagating your ideas into what a human would do, right? Is we have some idea when you, I don't know if you ever label data manually yourself. We do quite a lot. But so you might start out with the idea, I'm going to label this data point this way, that this is a, so we're doing radio stuff, we might, look, this is a clamp, I don't think this is a clamp, should we call this a clamp? You start discussing with your friend, and then as you go along further in the data set, you realize I'm labeling differently now than I did when I started labeling from the beginning. So you have sort of propagated your first ideas of what a clamp was into the unlabeled data. And the same thing here, right? If you have enough unlabeled data, you might have an idea, I think this is a clamp, this is not a clamp. And then you figure out, oh no, these two ideas clash, they don't merge together. So I have to change my idea of how the world works. That's an idea anyway. I don't think anyone knows exactly why it works.
Question. Like the first naive take will be to first do the training with the label data and then use this process for new data instead of doing mixing dynamically as you're doing it. Is there any reason why?
In the beginning I did what you're saying. So I did just as a warm-up, to warm up the model, I started training on just labeled data. And then after a while I switched off and started doing MixMatch. Right, and I think that should be a faster way of training. So I doing first warm-up with only supervised data, and then switching to using the MixMatch as well. So you do maybe 10 epochs or something of supervised training, and then you start doing semi-supervised training.
So what's good about this one? Why do you do the mixing?
Because you get better performance.
To do better performance. That was my question.
Yeah. I can have an add on there. So the idea was just using the plain right predictions as labels, right? That's sort of the main supervised.
Oh yeah.
So if you have a neural network and you have an unlabeled data set point, and you run it on that one, and have that as a ground truth label, and you then run it again and compute your loss will always be 0, because it's already the prediction of the network.
Yep.
So that's why you need some more sophisticated techniques. So then there are some naive ways of just having historic values of updating the network. But the naive approach doesn't work because you'll always get no gradients in your network.
Yep.
That's sort of the why. And then there are several methods, and MixMatch is sort of
you are
one
right.
way of getting around it.
But there are two things they do with the labels, right, that make them different from the original predictions. And it's that they do the averaging over many augmentations on the same image. So that means that they are forcing the network to be invariant to the augmentations, right? So they want, no matter what prediction you make on this image, if it's augmented in any way, you want it to be the same prediction. So that's one thing. So even if you don't do sharpening, it will still try to make it augmentation invariant, right? And then the second thing is like forcing it to be more certain of their prediction than they actually are, and then you'll get a gradient from that. Yes.
Is the proportion between labeled and unlabeled in the future effort is fixed or is also dynamic?
Sorry, I don't hear.
Is the proportion between labeled data and unlabeled data is also dynamic or it's fixed?
No, it's fixed. It's fixed. But do you mean during training, or do you mean in the original data?
During training. I mean, if you
I've done fixed, but I guess in the case where we did warm up on supervised first and then switching to MixMatch, then I guess we have a step function. Yeah, true. Okay, but so then what we might try here is we can use different hyperparameters to choose how many of our normal training data set with supervised learning, how many in each batch, how many of those do we want, how many of our guest labels do we want to train on that have been sharpened on average. And then we can use mix-up, like normal supervised mix-up, where we take a supervised image and a supervised observation and we mix those together. And then we can have supervised with unsupervised, which is what we're after, right? And then in MixMatch, remember that we have asymmetrical weights on the images. So we're prioritizing the first image over the second images, right? So we also have the unsupervised, supervised. So the reverse semi-supervised data set. And finally, we have unsupervised mixed with unsupervised. Yeah. And then, so in MixMatch, they don't actually separate these two and these two. They're calling these two the supervised and these two the unsupervised. And they have cross-entropy loss for those two, and mean square error for these two times 100. Yes. I only used cross-entropy for everything.
Can I ask, so for the unsupervised data set here, we have images coupled with our prediction, our pure prediction. Is that the case?
Here?
Yes, that data set contains a pair of an image and a prediction.
Yeah.
And the prediction is just the network's current prediction. At each epoch, it's a current prediction.
Exactly.
Okay.
They did do exponential moving average on the network, so they kept like an old version of the network, so all the old weights, and they exponentially decayed them to the latest, and they didn't get any better results with that, so I haven't tried using it. But I got my best results using like a hyperparameter search and a mix of all of these data sets. But as a fun a graph to look at, I made a graph where I only used supervised, or I only used supervised mix-up, and I only used mix-up semi-supervised. And like someone said before, of course we can't do just unsupervised, because then we don't have anything to start out with, any ground truth. So yeah.
Did you get a feeling of how much is the importance of doing the mix-up between two images compared to how much is important instead to do the label smoothing and label sharpening?
Sorry, how important is mix-up compared to sharpening?
Yeah. So there are two factors here. The fact that you take an image for which you don't have the prediction, you pass it through the network, and whatever output you get, you sharpen it a bit, and that's your new label.
Yeah.
and so you can do this on a single image, or you can do this on top of the mix-up of two images. And so my question is, what is more important? Is it more important that you do use the network to predict an image and then sharpen it, or use the network to predict the mix-up of two images and then maybe sharpening is not even so important? What's the most important?
Yeah, I started out doing only semi-supervised without mix-up and didn't get any good results at all. So I think doing only sharpening doesn't work that well, at least if you're doing, I mean, Mean Teacher is doing that, but they're doing exponential moving average on the old networks as the teacher model. But for me, I didn't get it to work at all. So, but when I added mix-up, it worked much better. But then sharpening started working for me. So when I started sharpening after having mix-up, it made a lot of difference. So I don't think it's just like independent components. I think they synergize a bit.
So sharpening alone doesn't work?
People have had success with it, I think. But I didn't get it to work anyway.
Okay.
But it might be that I'm using the latest model all the time. But the other guys have used like a teacher model that have old weights in it. Okay, so
I guess about that. So in the table in the study, they did that ablation thing, and they have the error without sharpening against the error without mix-up. Yeah. So doesn't that answer his question? At least for that sci
which part are you talking about right now? Sorry.
So the third row.
So they tried removing sharpening here.
Exactly.
Yeah, but they didn't do
Isn't that mix up?
Sorry?
So the second thing is mix-up. You remove the mix-up.
The second thing, no, here we have without mix-up. Yeah, so it's really bad, right?
Exactly.
It's quite horrible. Yeah. But that's a very interesting table to look at. Let's see. So here we have the just using the supervised, the green, and the orange is the mix-up supervised, and finally the blue is the mix-up semi-supervised. And like I said, the best model I was able to get on different categories, depending on the number of average image across, was a mix of all of the different data sets. But this was an easy graph to make. Yeah. And this is the test categorical accuracy, because I'm using the validation data set. I'm using those images, but I'm throwing away the labels, right? So I can't trust that I have sort of trained on the validation data set. So this is the test categorical accuracy.
Yeah. So can you explain what hyperparameters mix-up semi-supervised corresponds to exactly?
It's only this case.
And you said that if you would use a bit of everything, just uniformly, or
not uniformly at all, but I did like a region optimization, and I got a strange mix of all of them, and I can't really explain. But I haven't put that much time into it, trying to understand it. Yeah. Sorry. No. Yeah, well, we can see that MNIST is quite an easy problem in that already after having like 19 images, the supervised model is able to get like 95% accuracy with just using augmentation, the simple augmentation that we did. Yeah. So I think you need a more difficult problem to really see, like with Sci-Far or Street View house numbers or something to see the changes they saw.
Can you just read the labels because I can't see?
Yeah, sorry. The green here is the supervised, the orange is mix-up supervised, and the blue is MixMatch, or semi-supervised mix-up.
And I guess what you want to highlight here is that all the way to the left, where you have one sample per image, the difference is enormous.
Yeah, it's like 60% accuracy compared to 80% accuracy.
Again, in all these experiments,
It's
So the supervised maybe it's 10, the unsupervised is 100, the semi-supervised is 300. So the difference might not be because of the algorithm itself, but because of the training sample.
Wait, I don't know. What do you say? What's different? What's what we have 300 of?
For each experiment here in this comparison, I think each experiment run across or against different number of training instances.
Yeah, yeah. No, like in this here we get more and more images in the data set, and it's the same for all of them, right? So they're comparable in this. So we're increasing the number, we're making the problem easier and easier by adding more labeled data, and we're seeing what's the difference between these models when we're adding more labeled data. So if you have like, if you want to decide, should I invest money into labeling more data, you might want to have like, okay, but how much do I expect to gain in performance by adding more labeled data compared to doing something like MixMatch?
Just if I understood it right. So when you do this mixing, you always use like labeled data for that. So you would have two labeled pictures in this.
Not always. We like a lot of the cases. I had quite some of these mix up unsupervised, and also mix up like normal, so just unsupervised data in the when I did hyperparameter search, and that's what I did in MixMatch as well. They had the same number of these two and these two. I mean, of these two and these two. Right? So they didn't like specify this as different hyperparameters. They just took the same number of images that are labeled, the same number that are unlabeled. They make a copy of it. They mix them up, and then they merge these together. So they don't know how many they get of each of these. So it's stochastic each batch.
Okay. And then you use it to this mixing to tune the model, but you're not like producing new data that you label. I mean, in the end, there wouldn't be labeled data that is mixed. If you understand what I mean.
In the end, what do you mean in the end? This is just what we're training on. When we're using it in production, we're just going to input like the supervised data, right? Or the unsupervised.
I meant like later on you label more and more of your data.
Do we? Not necessarily, but sure, yeah. I mean, like in some cases, okay, so this is an interesting use case. Might be that you're training a model, and you're only able to train it here. But then when you're implementing it, you have to implement it offline maybe or something. So you can't get maybe the data from there to label it by yourself and then update the model like remotely. So you might have to train it. Sorry. What I'm trying to say is you might not be able to label the data in production, for example. So you could maybe train on the unlabeled data that you receive. So if you start off training in this environment and you move it to a slightly different environment, it still works okay but not great. And then you can maybe train on the unlabeled data in the new environment to make it perform better in the slightly different. I mean, I think that's a really cool use case that could possibly work. Okay, was that enough about? But basically, this is all the code that's sort of needed to do this, and I think the code for mixed-up data sets is just these three functions basically. So it's very simple to try out. Yeah, and yeah, we started looking at this table a little bit, but.
Can you say again what part is MixMatch and what is MixUp?
In my stuff?
No, the concepts. What's the MixMatch part of the algorithm and what is the MixUp part of the algorithm?
Mm-hmm. In my code or in this?
In this, yeah. Just
in this, okay. So MixMatch is using both averaging, sharpening, and MixUp, right? Those are the three, basically, right?
And MixUp. And MixUp.
And MixUp is just a component of. Oh, so that's just mixing the one image with another image, and their two respective labels as well to get a new image and a new label. like we did with the example in the code before. Yeah.
Do you sharpen after mix-up? Or is that only when you do the data augmentation that you sharpen?
Yeah, that's when we're doing the predictions. So when we're doing predictions, we haven't done any mix-up yet. So the mix-up is first when we're merging the two data streams in the end. Yeah. Yeah.
But you don't
Good
sharpen
question.
again after that? Then it's okay
no,
to have 50-50
no.
labels?
Yeah.
Did you later try this out on more complex types of images?
That's the plan, to use it at work as well. But yeah, we have only done like unsupervised attempts at the problem we're looking at. But this is the next one in the pipeline. Yeah, but we can see, like I said before, like sharpening on its own didn't help much, and then adding averaging helped over different predictions. They didn't get anything out of exponential moving average. Mix-up on its own was quite good. Yeah, you can have a look at that again later if you're interested, I guess. Yeah, so maybe I should. Yeah. So semi-supervised learning. I think the potential of semi-supervised learning is really cool. It might not be at the greatest heights yet. I mean, it's still research. So if you're going to try it out yourselves, be aware that be reasonably optimistic, I guess. I think it's useful. You can expect it to be most useful when you have very little data. A problem with that might be that most of the cases when you have very little data, you also have imbalanced data sets. So you might have to do some sort of weighting of your batches, so you get interesting data points in your batches. Yeah. But basically, it might be expensive to label more data. Yeah. And I talked about Kaggle before, I think. So if you're doing a Kaggle competition, maybe an extra percentage of accuracy or something can make a big difference. Like normally, if you're working, maybe 1% isn't enough to warrant 2 weeks extra work. But when you're doing a Kaggle comp, then yeah, it might be worth it. Yeah. But then remember that if you're training on the unlabeled test data set, then when you're using this in production later, you're going to have to train on the images that you want to predict before you predict them, which is kind of cool, but very slow. Yeah, the limitations now. I guess that in most cases you already have quite a lot of data, so it might be easier to just add more labeled data than trying to do semi-supervised learning. Yeah, there's also how do you mix up. Like in this case, we only talked about categorical data, where it's easy to see how would I mix up, weight together two different labels. But in some cases, you might have a regression problem instead, where you have, I'm predicting this coordinate, and in another label, I have this coordinate. And how would I mix those two together? I can't take the average of the two coordinates. Maybe you have to convert this to a mask or something, where you're predicting that there's a coordinate there and there in the mask instead or something. Yeah, I think you should, if you find it interesting, go try it out yourselves. I think it's really fun and cool. It's not that hard to implement, so it's, yeah.
Thank you very much.